we're gonna be discussing a new way of graphing, a new way of thinking about functions in particular. It's gonna change your perspective a little bit on what you think of as a function. In fact, you might be a little uncomfortable with what you're gonna see too as we graph something in a minute here. But this is still a function in the proper sense. We just have to generalize what you think of as a function. Here we have, for a parametric curve, we have a definition like this, where t is the dependent variable, or we might call it the parameter. And then we see that x and y both depend on that parameter. So instead of, like you're used to x and y being the independent and the dependent variable, respectively, here x and y are both dependent variables on t. So this will still be like a function, but you'll be like rejecting it a little bit viscerally because you'll be like, this doesn't pass the vertical line test. It can't be a function. So you'll have some of those reactions to seeing this, but we still have the idea of input and output. It's just the input here is a number, any real number, and the output will be an ordered pair of real numbers. So there are a couple ways to write that. One would be like how I've kind of illustrated it here. X and y both depend on t. Another way to write that same thing, you'll see us write this today, is to write x and y are both functions of t. So you can write it that way too. Maybe the functions, instead of being named f and g, maybe they're named x and y. And I'm using function notation to like emphasize that they're like taking a dependent variable t. In like, we don't use this notation as much as we ought to in high school, but sometimes we might say it like this too. The typical functions we're used to most of the functions you've worked with in high school are functions from the real numbers to the real numbers. So you might write them like this, a function that takes a real number and outputs a real number. Well, these functions are real from the reals to ordered pairs of reals. So sometimes mathematicians will write it this way: from reals to you won't ever have to know that notation, but if you want to look smart, you might write that. From the reals to ordered pairs of real numbers. Inputs are one number, outputs are two numbers. So let's try one and you'll get a feel right away for how this works. Here is what exactly I promised. I said that I would give you x and y, both of which depend on t via some function that I've given you. And I've given you two functions here. We want to think about this as one curve though. You give me a t, together these two functions output an ordered pair x, y that depends on your t that you chose. T is independent. These x and y coordinates are the dependent variables. So let's graph this together. Let's let t range from -3 to 1 and see what kind of thing we get. We still are going to be graphing this on the xy plane. And just like when we first encounter any new foreign function or mathematical object, we want to take it nice and slow. Let's maybe build a table, right? Like we don't have maybe any intuition about what this might look like. So let's just start plugging things in for t and see what we get. Again, x and y are going to be the outputted results. It'll be, like I said, it'll be like an ordered pair if you want. You can list it that way if you like. Okay, so if t is for a, we're going to let t be -3, for example. And if you want to step by 1, maybe we let t be these things, and just to try and fill out this table. You're also welcome to let t be -2.5 and anything else in there. But what happens when t is -3? What do you get? For example, if you plug them into the functions up here. 13 if there and 9 there. Can everyone confirm that that's what we get? So you can actually write it. I'll just write it that way. But of course, we want to think about that as the point 13, comma 9. So we'll plot that in a minute. But let's get another one too. -2. If you plug that in, get 8, comma 6. Okay, and just keep going down that chart and fill those out. Plug in -1 to both equations and tell me what x and what y you get, etc. Keep going. What'd you get for negative 1? 5 comma 3. And for 0, 0 and 1 is 5 comma negative 3. Okay, great. What did I get? 5, 3 on there. 5, 3 I need on there. Okay, so I think I'm doing a pretty good job of this here. I'll connect this. We'll do this in blue. How about? So if you start plotting these points, notice it's not obvious from the picture what t was. So you could even write in here if you like. This was when t was negative 3. This was when t was equal to negative 2. This was when t was negative 1, 0, and 1. And I'm going to do something now, which maybe you've already done. But we should just discuss the fact that we're allowed to do this. I'm going to interpolate a little bit in between. But if you doubt anything, if you doubt that these are all solutions in between, then feel free to check a few other points. I mean, we only checked with a t step of 1, but you could check negative 2.5 and see that it does lie, if t equals negative 2.5, the x and y values that are outputted do lie somewhere in here. But one way or another, are you okay with us doing that and making the curve like that?
Yes.
Okay. So you can find more points, but I think you're not too, it's not too much of a stretch to think that yeah we do have this nice smooth curve, and I think we've done it. For A, we're done. And then as you go on to do B, we want to, let's choose another color maybe. We can just kind of extend this table maybe. And we start, if it hasn't already been made obvious to you, you're starting to see a little pattern, aren't you? What's going on? What do we get when we plug 2 in?
You get an identical
8 comma negative 6. Yeah, I feel like there's some symmetry happening. If you plug 3 in, you get 13 comma negative 9. So I've done this before, I think. Yeah, so somewhere down here, and over here maybe. Not fun. Does that look right? Yeah, close enough. Okay. So for part B in red, I might graph, what am I going? From negative 2 to 3, so technically it'd be like from here, down to here or something, right? Beautiful, okay. And of course, we won't do C, but C would be the whole thing, the whole picture, if you kind of took the union of the blue and the red picture. You'd have the graph from negative 3 to 3. You'd be welcome to think about, well, what would it look like if you tried to do from negative infinity to infinity, right? Of course, what kind of shape do you think this is? Yeah, it's a parabola. This is a parabola. Again, a lot of you will be uncomfortable. I'm going to try to give you some disclaimers on the first slide. Some of you might be like, this is not a function. Well, if someone asked you, is this a function of x, you might say no. But this is still a function in the proper sense. We mean like we have an input, you give me an input, and I give you one thing as an output. It's just, in this case, the thing is an ordered pair. Okay? No problem there. So we're generalizing this idea of functions a little more than maybe you're comfortable with, but you'll become comfortable with it. Okay, we will get out the calculator, so have it at the ready. But let's actually, before we even graph this, let's see if we can predict what this will be. Okay. Notice also the curious way I've written this function. Right? Here I'm thinking x depends on t. What's the rule? Cosine t. Y depends on t. What's the rule? Sine t is the rule. Do you like how I've written it? You like that? Okay. I mean, it should remind you of something, right? Oh my God. It should remind you of something. And the reason I'm using that notation is to make you think of what we've been doing recently, and that's vectors. Does that make sense? So another word for a parametric function is a vector function, okay? A vector valued function. You give me a number, I give you back a vector. Would be a great way to say it too. Okay. So that's why this is like belongs in the same unit. It's not like we're turning over a new leaf or something. It's actually the same leaf we're still on. Still on. Same page. I guess if we're 21st century. All right, so can you predict what this will look like? Some of you are already like cheating, but if you let t be some various things, like the last one we just did by hand, didn't we? So like let's let t be some various things. If t happens to be, oh I don't know, 0, for example, what do you get? Cosine of 0, comma sine of 0, which is what? 1, comma 0. If give me another convenient. Now I'm out of convenient. Do you have a convenient value? Pi over 2, I like. Yeah. The fact that like pi is coming into the mix reminds me of some of the things we've done in our past life. So pi over 2, what do we get? 0, comma 1. What's another convenient value? And yeah, what are we getting? What are we getting? Pi over 4 would be a fun one to plug in. What are we getting now? Yeah, not just any circle. This is the unit circle. It's not just happens to be the unit circle. Remember, this is the definition of the unit circle, right? On your calculator, if you want to graph this now, if you haven't already pulled out your calculator, you should put it in parametric mode. And I'll do that too up here in front of you. And we're going to just stay here for a minute and play. How do I find my calculator? There it is. Okay. Mode. So go to mode and then go to, instead of func, go to par, which stands for parametric mode. And then now when you go to y equals, you'll have, instead of y1, y2, y3, you'll have 2 things, and then 2 more things, and then 2 more things. You'll have x1, y1, x2, y2, which makes sense based on like the thing we've just been talking about. That we need like 2 expressions in t to create a curve. So I'll type in these 2 for starters. Let's see cosine of t and sine of t. And notice that like until I've typed something into the second one, it doesn't even engage this. It won't let you graph just that, right? You have to have something in here. And as soon as you do, it's like, boop, I'm ready. I think now you put in 2 expressions. Now we're ready to go. Now before you just go and hit graph, let's go over and take a look at the window because there's something else to kind of give you a tour of here. Notice that all of the things you're used to seeing on the window are there. Your x min, your y min, your all that. But also at the top you have 3 additional controls you have. You have control over the t min, t max, and t step. So for example, if you typed in the example we just did, the parabola, you could do that by the way. Hopefully you'll get the pictures we had. For part A, we were going from t min -3 to t max 1, right? Stepping by 1 or something. So that would be you controlling for that a little bit. Okay. If you want a nicer picture, you might make your t step smaller though. So for this circle, what would be a good set of t values over which we'd like t to range? If our hunch is that this is a circle. What would we like? You were even giving me some values. You said 0. How about pi over 2? How about 0 to 2 pi? Remember, you can just type that into your calculator like that. And then the t-step, I'm just going to suggest to you, how about pi over 24 or something? Okay? Something small enough to make it nice. You'll see that if you make your t-step large, you'll get something kind of jagged because the thing your calculator is trying to do is it tries to guess that in between every point that it calculates, every 2 points it calculates, it assumes linearity, right? That's a bad assumption. We know that. So make it real fine. The trade-off, you can make it really, really small. Make it 0.00001 or something, and then it'll be a perfect graph. It'll be beautiful, but it'll take forever to graph, right? So that's the trade-off. All right, let's take a look here. I'm interested in maybe messing with x min and max 2 and all that. Maybe make it -2 to 2, and I don't know, -1.5 to 1.5 or something. It's the unit circle, I think. So let's see. And if you want it to be perfectly square, you can do zoom square, number 5. Okay, so there it is. It is in fact circular. And would you get the picture back there? You like it? Okay. Some of you are already playing. I love that you're playing. Let me give you some directions for your playing. Okay. Go back to y equals and try the ball instead. Have you done this before? Go over here. Press enter twice. How do you like that? You like that? And now when you graph it, you've got a little ball going around. That's kind of fun, yes? Okay. And the reason that I think the ball is fun here is help your neighbor get the ball if they haven't gotten it yet.
What I graphed it just
Huh?
looks like a little pencil.
Yeah, go over here. Go over here and press enter. You have all sorts of different modes you can get. Okay? Hey, can I ask you a question? Can I ask you a question? What would I need to do? What do you think would happen if I put in a 4 pi here? Yeah, now the reason I want to have that ball here right now, we're going to see whether you're right here, is watch this thing go. If we were just graphing in Cartesian coordinates, you'd be like, it's a circle, end of the story. But with this extra parameter, we also have like some other information. We also have a sense in which like there's like a time element, right? There's like, when is it in a certain location? Which is maybe why t is a good name for the parameter, actually, right? Because like a lot of times we think of this as like a curve, and we're at a certain xy value at a certain time, t, right? So that's like maybe a good way to think about it. So notice that like if someone just showed you this picture, you'd be like, it's a circle. But the information afterward is lost. That actually, wait, hold up. I want you to know I went around that circle twice. You know, we can maybe say something about that too. Which makes me think like, could I go less than 2 times around? Like, what if I wanted only the part in the second quadrant? What would I have to make t min and max be here? Yeah, how about pi over 2 to pi? Is that going to do what you just said? Just give you the second quadrant piece of that circle? Yeah, that's fun. What if we wanted this to go around the other way around the circle? Could we make that happen? I'm going to modify the equation maybe here. How about that? Yeah? Lots of things you can do here, and I will. Yeah, you get some interesting stuff. And we'll engage in the next slide in some really crazy explorations as well. Justin, do you have a question, or someone over there? Jeremy, go ahead. Okay, I'll come visit you. Make sure you're in radian mode. That might be the thing. Yeah, help each other out there. Make sure your calculators are all generating these pictures. All right, well, we'll come back to that circle in a minute. It's obvious that you guys are interested in playing, so let me give you some directions for your play. Here are some fun ones to try. Definitely encourage you to try the Lizardue figures, like these down here. And just play around with this and show off to your neighbors what you're getting. Call me over if you come up with something cool. That's awesome. Yeah, check it out. In particular, maybe you don't just like hammer stuff in. You also try and like gain some understanding as you're doing this. In this new context, do I know how to like take a graph and dilate it in the x or in the y direction? Do I know how to translate it? The answers to those questions are not too far off for you. You just need to think about it a little bit. And also, what about I don't know, could I rotate something in this new context? Or like, I mean, there are all sorts of questions I have now, right? So ask them and play, and show me if you get something cool. So I'll give you like just, I don't know, a couple minutes, just come up with cool things. I have some suggestions. Please don't just stick to my suggestions, though.
I did this. Exactly what it was. I think I actually did sign it. So frustrating. I need to do it. What's this gonna do? It's cosine of cosine of cosine cosine
I broke the universe. The hourglass.
It's the last one.
Actually, something that can't run out of words.
I didn't any of it.
Oh my god, Maddie, I hit it. What?
What's your windows at?
They don't want to stop. I'm in live. I think I heard him in live.
It's like that presence.
Let me emphasize again that you need to mess with your T-step a little bit and maybe your T-minute max. If you make your T-step really small, if you're getting something spiky, it's probably because, it's probably not spiky in reality. You might want to make your T-step a little lower. That will make your curve more curvy, and it won't be as spiky. But it might take longer to graph. That's the trade-off here. So play around with that. If it's still spiky, you use 0.1, and it's still spiky, try 0.0.
I think it's just gonna keep going.
You have your window going from high to high. Why are you doing that?
Well, they're like, it becomes terrible.
Are we having fun? Are we having fun?
I am having fun. It's a lot of fun. This is entertaining. Thank you for showing us. It's like the algebra white when you figure out how quadratics work.
There we go.
Oh. Yeah, I can make the universe.
A bigger forever.
What the hell?
There we go.
The spiral universe makes sense.
Oh, hey, by the way, useful information. If you ever want your calculator to stop graphing, you press on. Okay.
No, I never wanted to stop.
Yeah, I had that problem.
Well, sorry, I should have told you that a long time ago.
You said it's a
All you have to do is stop it and the one you can. So if you do that in math, right, enter times 20 it's just a random, it's just a math, right, times 20.
Oh crap.
We're minus all you do. There you go.
No one likes.
That's what that
That's just like really. Oh really? Yes, I can get you.
Oh yeah.
What? This is what? How is it so wide? What? This is not an overcomplicated thing. What is wrong with you people? Quadratic and it just makes it nice. You know? Wait, you stack them all? Is that how you get like the crazy shape thing? How do you get the super shape? How do you do that?
Alright, so feel free to play around with these some more. You know, if you're ever bored in English class, or you can be doing this. Wait, I have another question. So I have some questions of the type that I know you guys are having fun playing, but I want to go back to this circle real quick and ask some like kind of basic questions that we haven't asked. So let me ask you a couple questions. So first of all, could we? I asked these a second ago, but no one gave an answer yet. Could we do like a shrink on this in all directions? Can we make this a circle like radius 1/2 maybe? How would we do that? Yeah, what do you think, Sue? Yeah, so let's see if that works here. Oops. Let's see if that gives you the right picture here. All right, so is she right? Yeah, now we have a little circle of radius 1/2. Actually, it looks like a hexagon, kind of. Octagon. Can you, what about this? Well, okay, so I think we might understand how to dilate in one direction or another. Do you know how to reflect? Do you know, this one's not very interesting for reflections, but Is it clear how you might reflect something in X and Y? I mean, think about actually the physical process of plugging numbers in. Like, how did that happen? What would you have to do to make that flip? What about translation? What if we wanted this? Let's say we want to translate this picture. I don't know, right 1 unit. Instead of having it be centered here at the origin, I'd like it to be centered at the point 1, comma 0. How would I have that happen? What do you think? How can I modify these equations?
If you write -1.
So instead of
only on the x, so you only want to move the x direction.
yeah, we want to move like the x coordinate. Like think about how we build these. We want the y coordinate to be unchanged, and we want the x coordinate. Like we're happy with y at all times t. We're happy with y, but we'd like x to come out to be the same thing it is, but 1 unit bigger maybe. Does that translate it to the right one? Could you translate this left 3 and up 5 or something? Sure, yeah, you know. So do what you like to modify this. There's a lot of cool stuff we can do here. Right? Okay.
When you add to this one, it moves to the positive direction.
Yeah, can you think about why that's happening? I mean, think about actually, if you were to plug in 0, for example, does it work? Yeah, it just kind of works, right? All right. So feel free to play around with the graph later some more sometime. I don't have anything else right now, at least, to say about the calculator. We will soon, but I'd like to turn our attention to some other things we might be able to discuss in parametric land. One thing might be a result of a conversation you might have been having with yourself. You're like, hey, that thing we already did with the parabola, this circle we just did, it seems like, in some cases at least, some of the ones we just did, maybe not, but in some cases it seems like this is something familiar. Could I kind of bring it back to the world of Cartesian coordinates? Could I algebraically show myself that this really is just whatever, a circle or a parabola or something? So let's try that here. Can we actually just take this from parametric form, which is how this is kind of given, and put this back into just x's and y's with no t? It's just like a little bit of an algebraic exercise. Keep in mind that this is like, I mean really, this is like a system of equations, 2 equations and 3 unknowns. So it's kind of like a slightly underdetermined system. Maybe we can eliminate one of the variables, right? What is the attack method here?
Elimination.
Elimination, how do we do that though?
You make the t's equal.
Yeah, maybe we could set the t's equal to, somehow we need to get rid of one of the t's. My route might be like substitution. I might solve one of these for t. Maybe the easier.
Could you use elimination and multiply by 2? And then eliminate the t's?
Yeah, you do whatever you want to do to get rid of t. So I like substitution, that's why I'm like going for that. So t is also known as y minus 5, apparently is another perfectly good name for t. So now I can write this equation over here as x equals 4 minus 2 times y minus 5 instead. And actually, I mean, we might clean this up a little bit now, but we've done it. I mean, have we eliminated the parameter? I think we have. Do you see t? I don't. All right, so we'll keep going and clean this up, but we've done the task that's been asked of us. T is gone. And this might be something that we know. Well, what is it, of course, even before we clean it up? Yeah, it's a line, right? It's got x's and y's and no exponents. Let's see what this looks like here. We got 4 minus 2y plus 10. We got 2y equals negative x plus 14. So I'm getting y is equal to negative a half x plus 7. So there we go. We eliminated the parameter, and feel free to graph this on your calculator, but you're welcome to graph this in parametric mode. What I'm expecting now, I have an idea now, what I'm expecting to see if you graph this in parametric mode is a line of a type that I know lots about, right? It's got a slope of negative a half and a slope of 7, and a y-intercept of 7. Like I think I know what this is going to look like if you go into parametric mode and graph this. Now, keep in mind, what did we lose? Like you might be thinking like, okay, well, why bother with this at all? Well, first of all, there are lots of cooler things you can do than lines with parametric mode, you just saw. But also, this keeps track of like time information, and when we've done this process, when we eliminate the parameter, we've kind of also gotten rid of the time information. You know, we understand the set of locations of the particle that it once traveled. We see its path. we no longer know where it was at a given time, which might be meaningful in a particular problem. So there are trade-offs here, and the interpretation might be a little different on both of them. But certainly the path is described. We just saw it in terms of x and y. So let's try another one here. I've written in another kind of nice way here, right? You like how I'm writing these? Okay. Trying to expose you to a couple different notations that might be available to us. But you're also welcome to just write it that way. That's exactly what we mean here. And again, the goal is to eliminate the parameter. So what do you see? And I guess that's it. I guess you're done. I might solve for t over here just because it's easy. I'll finish this one off here as you're leaving. Yeah, come show me a good one if you have one. Bye, everybody.
I'm sorry.
Steven, you ready for this?